Hi everyone. In this video, we are going to be going through a worked example encompassing everything we've learned thus far, which would be assignment of frames, DH tables, and finally transformation matrices. So let's get into it. If you guys like this video, don't forget to give me a thumbs up and please subscribe. I'm Chums and welcome to ThatsEngineering. Alright guys, so this is the robot that we will be looking at. Now forgive my sketching, I know it's not perfect, but what I've tried my best to show you is a robot with 3 revolute joints, where this would be the first joint, this would be the second joint, and the third joint, each having their own angle of rotation, theta. L1, L2, L3 would be the distances or the link parameters, and this would be the tool which already has its frame pre-assigned. Now there are 4 steps that we will be looking at. The first being frame assignment, and this will be done for the 3 joints. From this we will look at making the DH table, and from the DH table the transformation matrices. And this can be done using the equation we have learned. And from the transformation matrices, we can do any matrix algebra to find any unknowns that we don't know. In this case, we look for T0, 3. Alright, so the first step would be frame assignment. Here we will be using the 6 conventions we learned, and we'll start off with identifying the joints and their joint axes. So we have the first revolute joint here, the second revolute over here, and the third joint over here. The first would have a joint axis sort of something similar to this, running vertically. The second would be here, and the third would be here. Now something to note is that joint 2 and joint 3 are actually parallel to each other, just that the way I've drawn it, it looks slightly different. Now we can assign the direction for each of the joint axes by considering the theta value, and to do this we would look at our right hand rule, where the direction of the fingers would point in the direction of theta, and the thumb would show where the positive axis is. And if you use this for joint axis 1, it should point in this direction, 2 would be in this direction, and 3 would also be in this direction. We can now assign our z axis to our 3 joints. So we would have z1, z2, and z3. Right. The next step would look at assigning the origin for each of our joint axes. Now again we will consider I and I plus 1. So when we look at joint 1, we consider joint 2. As the 2 joint axes intersect, the point of intersection becomes the origin for the first axis. So z1 would intersect at this point, and so this would be the origin. For 2 to 3, since they're parallel, we will look at the common perpendicular which lies along this particular link. Therefore, the origin of z2 would be the start of the common perpendicular, which would be the start of the link. So z2 would lie in this direction. Right. Then to set z3, we will consider the next frame, which is the tool. Here they are both intersecting with each other, as ZE has this sort of joint axis. The The intersection point is over here, making that the origin for Z3. Right. So now that the z-axis and the origins have been set, we can look at setting the x-axis. Now, if the two axes intersect, we look at the intersection of the planes, and the x-axis would be normal to that. If, however, the axes are parallel, x would lie along the common perpendicular. So, again, from 1 to 2, they intersect. Henceforth, we look at the planes. So the plane here would be something like this. So if I draw it out separately, you will have one plane here and another plane over here. And so x would be normal in this direction. And that just so happens that it is along the link. This link. So x1 would be along this particular link. Now from 2 to 3, they are parallel to each other, so x2 would lie along the common perpendicular, which also happens to be at the link. So x1 and x2 would coincide with each other along the link. From 3 to the tool. Here again the two axes intersect, so it's a point of intersection. So we look at the intersection between the two planes. In this case, the Z3 plane would look something like this, while the ZE plane would look something like this. So this area pointing upwards would be the x-axis. So therefore, from this point, x-axis would point upwards, x3. So again, you can see that x1 and x2 are sort of opposite to the direction of rotation theta 2, while x3 is opposite to the direction of rotation theta 3. That is why we know it points upwards. Now we don't really need to find the y-axis because it's not needed for the calculations. The frame for the tool is already given, but what we can do is find the base frame. Right, so this marking here shows that this is the base frame, so we can assume the origin of the base frame would be at this point. We will assign the base frame arbitrarily, but we will do so to closely match the first frame. So Z0 would be along here, and X0 would be in this direction. Alright, so the second step would be to find the DH table using our 4 link joint parameters. Here, when considering the axes, we move from one to the others. So we would go from 0 to 1, 1 to 2, and 2 to 3. So considering the first case, 0 to 1, for the first two parameters, I would be equal to 0. And for the next two parameters, I would be equal to 1. So for ai minus 1, we would want the distance from z0 to z1 along x0. So the distance between z0 and z1 along x0 would be 0, as they are both on the same line or the same line of action. For our alpha I minus 1, it would be the angle between z0 and z1 about x0. So as both z0 and z1 are pointing in the same direction, the angle would be 0, because it would look at the angle that z0 has to rotate by to match up with z1. Then the distance between x0 to x1 along z1. So the distance from x0 to x1 in the z1 direction would be L1. Now this value would usually exist if it was a prismatic joint, but in this case it's a revolute joint. However, the value still exists due to the offset created by the link structure. And the final value would be the angle between x0 and x1 about z1. So if x0 was stationary, x1 could rotate in relation to x0 about with an angle theta 1. So this value would be theta 1. Now let's have a look for the next set of axes. Right, so now we will consider axis 1 to 2. So for the first two, I will be equal to 1, and for the last two, I will be equal to 2. So for ai minus 1, we would want the distance between z1 to z2 along x1. So the distance z1 to z2 in the x1 direction would be 0, as they both have the same origin. Then the angle z1 to z2 about x1. So in this case, the angle z1 must rotate to match up with z2 if rotated about the x1 axis, which is in this direction, and z1 would actually have to rotate by this amount 90 degrees. So it's actually 90 degrees counterclockwise. So because of that, it's positive. So the usual convention that we use is if we have a counterclockwise rotation, it's taken as being positive, while a clockwise rotation is taken as being negative. This is just a convention that we normally use. So that's why the sign here would be plus 90 degrees. Right. For I equals 2, we want the distance from x1 to x2 about z2. So in the line of z2, the distance or the offset of x1 and x2, they're both on the same line and they both have the same origin. So this offset would be 0. And finally, we have the angle x1 and x2 about z2. So that is, if x1 is stationary, how much x2 can rotate about z2. And the value for that would be theta 2. Right, so now let's have a look at the last set of axes, which is from 2 to 3. For the first two parameters, I would be equal to 2, and then I would be equal to 3. For ai minus 1, we want the distance of z2 to z3 about x2. So that is the distance between z2 and z3 in the x2 direction, and that distance would be the length of this particular link, which is L3. Then for alpha I minus 1, the angle z2 and z3 about x2. So that is the angle that x2 would have to rotate to match up to z3. I'm sorry, the angle z2 would have to rotate to match up to z3 if rotated about x2. That is anywhere in this direction. As they're both pointing in the same line and are parallel to each other, this angle would be 0. For the next two parameters, for di, we look at the distance between x2 to x3 about z3. So the distance between x2 over here and x3 over here in line of z3. So this distance would actually be the length of this particular link over here, which is L2 as given. But z3 is pointing in this direction, which means this direction is positive. And since we're moving from x2 to x3, we are moving in the opposite direction. So this value would be negative L2. The final one is a bit tricky, but let's have a look at it. The angle between x2 and x3 if rotated about z3. So first of all, let's have a look at it. z2 stays stationary, and if z2 is stationary, relative to that, x3 can rotate by some angle theta 3. So we have a theta 3 term here. In addition to that, the amount z2 has to rotate to match up to z3 about the z3 axis would be 90 degrees in this direction, because they both have to point upwards. So in addition to the rotation of theta 3, there is an extra 90 degrees. And this is true. If you look at it again, you have z2, which can rotate 90 degrees to match up to z3, and then z3 can rotate further by theta 3 degrees. So theta I in this case would be theta 3 plus 90 degrees. And that is the DH table. So something to note from here is that if you have a rotation, you will look, if the rotation is counterclockwise, it would be positive. If clockwise, it would be negative, and this is purely by convention. The second would be, if you want to identify if a rotation is clockwise or anti-clockwise, you would look at it from over here. So by looking at it from this side of the axis, a rotation in this way would be counterclockwise, while a rotation in this direction would be clockwise. Alright, so the next step, which would be the third step, is to find the transformation matrices. And this can be done using this equation, where you can directly plug in the values and find your transformation matrices. So first we have t 0 to 1, because we moved from axis 0 to 1, 1 to 2, and 2 to 3. So for t0 to 1, we will use the first row from our DH table. Okay, you have cos theta I, which would correspond to cos theta 1. Then it would be minus sine theta 1, 0. AI minus 1 is also 0. Right. Second value, sine theta 1, cos 0. So it would be sine theta 1 when simplified. And this would be cos theta 1. You would have 0. Cos sine 0 is 0. And the second value would also be 0. Again, 0 sine alpha I minus 1 is 0. So this whole term goes to 0. This whole term goes to 0. This term would become 1. And this term would become L1, because di is equal to L1. And 0, 0, 0, 1. So again, as we saw in the first few videos for this playlist, this is a rotation around the z-axis and shows the orientation of the manipulator, while this shows the position of the manipulator. And you can see this term L1 here is on the z axis. So you have your px, py, and your pz, and this matches up because the first joint, which was over here, the first joint which had its origin somewhere here was L1 away from the base in the z direction. So that is why this L1 is over here. So it makes sense. Now let's have a look at T02. Right, T, so it would be 1 to 2. Right, t1 to 2, we use the second row values. So cos theta 2 minus sine theta 2, 0. ai minus 1 is also 0. Then we have sine theta I, which would be sine theta 2 into cos alpha I minus 1 would be cos 90. Cos 90 would be 0. So this term goes to 0, this term goes to 0. Minus sine 90 would be negative 1, and this would be 0 because di is 0. Here sine theta I would be sine theta 2, while sine alpha I minus 1 would be 1. So sine theta 2, cos theta 2, cos 90 0, cos 90 0, and 0 0 0 1. Right, so you can solve in a similar manner for the last set of axes, which is 2 to 3, and you would actually have theta 3 plus 90 degree terms. For example, cos theta 3 plus 90 and sine theta 3 plus 90. And if you were to simplify all these terms, you should get this matrix for transformation matrix of 2 to 3. The next step, which is the final step, wanted us to find the transformation matrix 0 to 3. And we can do this by simply multiplying 0 to 1, 1 to 2, and 2 to 3, which is what we found in the previous part. Alright guys, so that's all for this video. If you guys liked it, don't forget to give me a thumbs up by clicking the like button below. If you have any questions or clarifications on the work I just did for the direct kinematics section on robotics, please feel free to leave a comment and I will do my best to get back to you. I hope this video helped, and if you haven't done so already, don't forget to click that subscribe button. Thanks everyone, and I'll see you all in the next video.